a cinematic descent into the paradox of time, the river that carries all things forward, never ceasing, never reversing. From galaxies spinning to the ticking of human hearts, time's current is thought to move in only one direction. Yet, hidden within physics are strange whispers, equations that make no distinction between past and future, particles that seem to disregard the arrow of time, cosmic phenomena that hint at flows beyond comprehension. What if time does not only move forward? What if, in hidden realms of the universe, the river bends, loops, or even flows backwards? To imagine such a reversal is to question causality itself, to unravel memory, and to confront whether the universe is built upon a deeper order where time is not what it seems. This is not fantasy, but speculation grounded in science, in entropy, relativity, and quantum mysteries. A haunting possibility emerges, that the arrow of time is fragile, and that somewhere in the vast cosmos, a current flows against it. Time has always been the most intimate and elusive of mysteries. Long before telescopes probed the galaxies, before equations bent the structure of space-time, humanity gazed at the heavens and asked the question that would haunt all ages: does time flow in a circle or in a line? The ancient visions of time for ancient civilizations. Time was not yet a river rushing forward, but a cycle repeating endlessly. The Egyptians saw time as eternal recurrence, the sun rising and setting, reborn each day in the sky. The Hindus spoke of Kalpa's vast cycles in which universes are born, destroyed and reborn, spiraling endlessly through creation and dissolution. The Maya etched into stone their great wheels of time, where eras spun in cosmic rhythm. To these cultures, time was not linear but circular, a wheel turning forever. The past returned as the future, and nothing was ever truly lost. But in the philosophies of Greece, another vision took shape. Plato described time as the moving image of eternity, a reflection of perfect order unfolding. Aristotle imagined it as a measure of change, continuous and unbroken. In these thoughts lay the seeds of linear time, a forward-moving thread stretched across existence. Newton and the absolute clockwork hit was Isaac Newton, who cast time into its modern form. In his Principia, time became absolute, an invisible stage on which all events unfold. It flowed uniformly, the same for all observers, never bending, never breaking. The ticking of the cosmic clock was steady and impartial, indifferent to the motions of the heavens or the hearts of men. This vision of time as absolute became the foundation of classical physics. The universe was a great machine, its gears turning according to laws of motion, all measured against the perfect metronome of Newtonian time. For centuries, this view reigned supreme. Einstein's revolution, but in the early 20th century, time was shaken from its pedestal. Albert Einstein, through his theories of relativity, revealed that time was not absolute after all, but relative and pliant, inseparably woven with space into a single fabric. Space-time clocks slowed near massive stars, minutes stretched aboard fast-moving ships, and simultaneity itself dissolved. There was no universal now. Each observer carried their own flow of time, distorted by motion and gravity. Einstein's equations were indifferent to past and future. In the geometry of space-time, time was a dimension like space, stretching in both directions. The river could flow forward or backward, and the laws of physics would not falter. This was the first fracture in the certainty of time's arrow. Entropy, the arrow, appears undyet. Daily life seemed to mock Einstein's symmetry. Cups fall, shatter, and scatter into shards. Never the reverse. Heat flows from fire to ash, never from ash to fire. We remember the past, not the future. The explanation came from thermodynamics. In the 19th century, scientists such as Rudolf Clausius and Ludwig Boltzmann defined entropy, a measure of disorder. The second law of thermodynamics declared that entropy in an isolated system always increases. This law gave time its arrow. Though equations were reversible, entropy was not. Disorder always grew. Stars burned their fuel, universes expanded, and the arrow of time pointed forward. It seemed that the mystery was solved. Time flowed from low entropy to high, from order to disorder. The river moved one way because the cosmos demanded it, but beneath this apparent certainty lay unease. Why was the universe low in entropy at the beginning? Why did it start in such an improbable state of order? Without that unlikely beginning, there would be no arrow of time. The quantum puzzle, as physics turned to the quantum realm, the mystery deepened. The equations of quantum mechanics, showing as wave function, the rules of probability, were perfectly time-symmetric. Reverse them, and the laws held true. And yet, the act of measurement seemed to introduce irreversibility. When a quantum system is observed, the wave function collapses, and possibilities vanish into a single outcome. The past and the future are not treated equally. Some interpretations, like the many worlds hypothesis, sought to preserve symmetry, while others accepted collapse as an arrow. Time in quantum mechanics was slippery, refusing to obey either Newton's absolutes or Einstein's relativity without paradox. The shock of CP violation, then came the laboratory hints that time itself could be broken. In 1964, physicists James Cronin and Val Fitch, working at Brookhaven National Laboratory, studied the decays of kaons, strange particles made of quarks. To their astonishment, they found that these particles did not behave the same when time was reversed. The symmetry of physics was fractured. Processes could distinguish past from future. This phenomenon, called CP violation, violation of charge, and parity symmetry, implied that the universe itself preferred one direction of time over another, at least in the realm of subatomic particles. Later, similar violations were found in bosons and other particles. The laws of physics, once thought perfectly balanced, bore an intrinsic asymmetry. Time's arrow, it seemed, might be written into the very interactions of matter. Hints from the cosmology, too, began to whisper of strangeness. The Big Bang appeared as the ultimate low-entropy beginning, the fountainhead of time's arrow. But what if the cosmos harbored regions where entropy decreased, where the arrow pointed in reverse? Some theorists speculated about mirror universes, born alongside ours, where time flowed backward relative to our own. Others wondered if black holes, with their strange horizons and singularities, might harbor reverse temporal currents. Even the cosmic microwave background, the relic radiation of the Big Bang, carried hints of asymmetry, anomalies, that some dared to interpret as signs of time's arrow bending differently across the sky. The stage is set by the mid-20th century. The picture was no longer simple. Newton's absolute time was shattered. Einstein's relativity erased universal simultaneity. Entropy explained the arrow but left unanswered why the cosmos began in order. Quantum mechanics blurred reversibility, and particle physics revealed processes that truly distinguished past from future. The river of time, once imagined as a steady current flowing endlessly forward, now seemed fragile, contingent, uncertain. Its direction was not written clearly in the equations of physics, but instead emerged from improbable beginnings and subtle asymmetries, and in that uncertainty a haunting possibility arose. Perhaps time does not always flow forward. Perhaps, in hidden realms, in quantum fluctuations or cosmic symmetries, the current bends. Perhaps there exist places, or even entire universes, where the river of time flows backwards. For centuries, time had seemed unquestionable, a current that needed no explanation. It carried every life, every planet, every galaxy forward, and only forward. But with the rise of modern physics, a quiet shock emerged, one that unsettled not only science, but philosophy itself. The reversibility paradox sat the deepest level of physics. The laws of motion make no distinction between past and future. Newton's mechanics, Einstein's relativity, Maxwell's electromagnetism, Schwive equation, all of them are time-symmetric. Reverse the clock, and the equations hold true. A planet orbiting a star could just as easily be described backward as forward. The paradox was stark. If the laws of nature were indifferent to direction, then why did reality itself insist on flowing only forward? Why do glasses shatter but never reassemble? Why does smoke rise but never collapse back into the match? Entropy, the second law of thermodynamics, gave a partial answer. The universe began in a state of low entropy, and disorder grows as time progresses. But entropy explained only the statistical tendency of systems, not the deep distinction. It was not written into the equations themselves. The river of time seemed to come not from the laws of physics, but from the improbability of the universe's beginning. For many, this realization was profoundly unsettling. The arrow of time, so absolute in human experience, was not fundamental. After all, the shock of CP violation in 1964, the unease deepened into astonishment. At Brookhaven National Laboratory, James Cronin and Val Fitch studied the decays of neutral kaons, fleeting particles born in high-energy collisions. According to theory, kaons and their antiparticles should behave as mirror images. If the charges were flipped and the spatial coordinates inverted, the symmetries known as C-charge and P-parity, their behavior would remain the same. And under time reversal, the equations should remain valid. But the kaons betrayed that expectation. Their decays showed a preference, a subtle but unmistakable bias that broke the symmetry. Time reversal symmetry was not absolute. Nature itself seemed to distinguish between past and future. This discovery, known as CP violation, was a turning point. The arrow of time was no longer just a statistical consequence of entropy. It was encoded, however faintly, in the interactions of matter. Itself, Cronin and Fitch won the Nobel Prize for their discovery. But the deeper implication lingered like a shadow. If physics itself could bend the arrow, then time's direction was not as inviolable as once believed. Causality, at risk the possibility of time reversal, shook more than physics. It threatened causality itself. Cause and effect are the pillars upon which knowledge stands. To say that the future could influence the past, or that time could reverse, is to pull at the thread that binds reason. If a particle could move backward in time, could an event be its own cause? Could the present be shaped by the future, rather than the other way around? In quantum mechanics, some interpretations already whispered such possibilities. The Wheeler-Feynman absorber theory suggested radiation might travel both forward and backward in time. In delayed choice experiments, the measurement of a particle seemed to determine its past behavior. Reality itself appeared malleable, as though time were less river than fabric, woven from both directions at once. These ideas were unsettling not because they were impossible, but because the equations permitted them. The laws of physics, stripped of entropy and observation, refused to enforce causality. The fragile arrow this was the true scientific shock. The arrow of time was not a universal law, but an emergent phenomenon. It was fragile, contingent, born of circumstance. Entropy gave it direction, but only because the universe began in improbable order. CP violation hinted at asymmetry, but in processes so rare that they barely touched the macroscopic world. For all its dominance in human experience, the arrow of time was nowhere written into the core equations of physics. Time, the most familiar of realities, was revealed to be the most precarious. The emotional weight of reversal for philosophers, the implications were profound. If time could reverse, then memory itself was suspect. The future might be as real as the past, and the distinction between them an illusion. The flow of time, so intimately tied to human identity, might not exist beyond the mind's construction. Even Einstein hinted at this in his letters, writing after the death of a friend, for us believing physicists. The distinction between past, present, and future is only a stubbornly persistent illusion. The equations confirmed his intuition. Past and future were equally real in the geometry of space-time. It was only entropy, chance, and perception that made the river flow in one direction. Time's arrow under-questioned the revelations, sparked debate that continues to this day. Is the arrow of time fundamental or emergent? Is entropy the true cause, or merely the symptom of deeper laws, yet unknown? Does CP violation signal a crack in time symmetry, or merely a clue to something beyond our current theories? In laboratories, physicists probe neutrinos mesons and quantum states, searching for signs of asymmetry. In cosmology, scientists ponder why the Big Bang began in such improbable order. Everywhere, the question lingers: why does time move the way it does? The deep unease for all its triumphs. Physics cannot yet explain the most basic of human certainties, that time flows forward, and in the gaps of that explanation, unease grows. If the laws permit reversal, then what prevents it? If the universe can harbor processes that break symmetry, then might there exist regions where the arrow points the other way? To confront these questions is to confront the fragility of order, the precariousness of causality, and the haunting possibility that the river of time does not always flow forward, but sometimes in hidden domains of physics or in vast stretches of the cosmos bends back against itself. This was the shock. The arrow of time, once thought absolute, revealed as a fragile construct, not fundamental but contingent, not inevitable but emergent, and in that revelation, the possibility of reversal became more than imagination. It became physics. The shock of time's reversibility did not silence science. It ignited a deeper search. If the laws of physics made no distinction between past and future, then where did the arrow of time truly come from? If entropy was its engine, why had the universe begun in such improbable order? If CP violation hinted at cracks in symmetry, what larger truth might those cracks conceal? The investigation stretched across cosmology, quantum theory, and the study of black holes, each domain revealing new fragments of a puzzle that remains unsolved. Entropy at the dawn of time. Roger Penrose, one of the great minds of mathematical physics, argued that the key lay not in the future, but in the beginning. Entropy, he observed, explains the arrow of time only if the universe started in a low entropy state. But why should it have done so? The early universe, moments after the Big Bang, was hot, dense, and nearly uniform. Yet uniformity is not disorder, but order. A random arrangement of matter and energy would have produced far higher entropy than the elegant smoothness of the early cosmos. In Penrose's view, this improbability is the real origin of time's arrow. The universe began in a state of extraordinary order, and every second since has been the slow unwinding of that perfection into chaos. The arrow, then, is not fundamental, but a consequence of an initial condition so unlikely that it demands explanation of its own. The black hole paradox: if entropy drives time, then black holes reveal its extremes. They are the great furnaces of disorder, swallowing matter and energy, erasing distinctions, reducing complexity to simplicity. Stephen Hawking discovered that black holes are not eternal prisons, but radiate energy, slowly evaporating over eons. Yet this radiation seemed to carry no information about what fell inside. If true, this would mean that information, the record of the past, is destroyed. Such destruction violates the principle of time reversibility. In Hawking's scenario, the past cannot be recovered from the future, and causality is broken at the event horizon. This information paradox remains unresolved, though many now believe information must, in some hidden way, survive. Whether in the form of soft hair on the horizon, or through subtle correlations in Hawking radiation, or encoded holographically on the boundary of space-time, the universe seems to resist the obliteration of memory, yet the paradox revealed a chilling truth. Black holes sit at the edge of time's arrow, places where past and future may dissolve. The CPT theorem, symmetry at the core in the abstract realm of particle physics. Another clue emerges, the CPT theorem. It states that if charge C, parity P, and time T are reversed together, the laws of physics remain invariant. This means that a mirror universe of antimatter, running backward in time, would be perfectly consistent with our physics. Nothing in the equations forbids such a realm. It may be alien to human experience, but it is as lawful as our own. The CPT theorem is not speculation, but proof, a deep symmetry of quantum field theory. It does not guarantee the existence of a time-reversed universe, but it insists that such a possibility is compatible with the very foundations of physics, quantum mechanics, and the blurring of past and future. Quantum theory adds further unease. At its heart lies the wave function, a mathematical object that evolves smoothly and symmetrically in time. But when a measurement is made, the wave function collapses, selecting a single outcome from many possibilities. This collapse appears irreversible, distinguishing past from future. Yet some interpretations, such as the many worlds hypothesis, insist there is no collapse at all. Instead, all possibilities are realized in branching universes, each as real as the next. In this picture, time does not flow in one direction, but spreads into an ever-branching tree. Other experiments, like the delayed choice quantum eraser, hint that present measurements can alter the interpretation of past events. In quantum mechanics, the distinction between cause and effect, between before and after, grows tenuous. Time begins to resemble a fabric woven from both directions, not a current flowing in only one. The role of neutrinos and mesons, the smallest scales, Experiments continue to probe whether particles themselves obey time's arrow. Neutrino oscillations, the strange transformations between neutrino flavors as they travel, may carry signatures of CP violation, extending the cracks first seen in kaons and bemesons. If confirmed, these asymmetries could explain one of the deepest mysteries of all: why the universe contains matter at all. In the earliest moments after the Big Bang, matter and antimatter should have annihilated in perfect symmetry, leaving only light, yet somehow matter gained the slightest edge. That imbalance, amplified by CP violation, allowed stars, galaxies, and life to exist. In this way, time asymmetry may be the reason anything exists at all. Without a preference for one direction, the cosmos would have dissolved into featureless radiation. The arrow of time may not merely guide existence, it may have birthed it, the early universe, a two-headed arrow. Some cosmologists go further, suggesting that our universe may not have one arrow of time, but a dot in this vision. The Big Bang is not the beginning of time, but a central point. From it, time flows forward in both directions. Two observers on one side, the arrow points as we experience it. Two observers on the other, it points the opposite way. Both see entropy increasing, both see themselves moving forward, but from each perspective, the other universe flows backward. If true, then the arrow of time is not absolute but relative, a feature of perspective shaped by entropy's expansion from a common origin. The puzzle of memory and consciousness even, as physics wrestles with symmetry and entropy, the human mind insists on forward flow. We remember the past, not the future. Our thoughts are anchored in sequences of cause and effect. But why should consciousness be aligned with entropy? Why should memory accumulate in one direction? Some philosophers speculate that memory itself is a manifestation of entropy, our brains encoding information as disorder grows. If time were reversed, perhaps memory would reverse too, and beings in that universe would be as convinced of forward flow as we are, though their forward is our backward. This speculation is not testable, but it underscores the strangeness of the arrow. It may not be a feature of reality at all, but of perception shaped by entropy. Deeper layers revealed the deeper science probed, the stranger the picture became. Entropy explained the arrow, but demanded improbable beginnings. Black holes threatened information and causality. Quantum mechanics blurred the boundary between before and after. The CPT theorem insisted that time reversal was not forbidden, but permitted every step into investigation revealed not clarity, but paradox. The arrow of time, so absolute in human experience, seemed fragile, contingent, and perhaps illusory. And if that were true, then the haunting possibility returned. Somewhere in the cosmos, the river of time may run backwards, carrying its worlds and its lives against the current we take for granted. The deeper physics looked into time, the less secure its arrow became. What began as whispers in equations grew into visions of entire universes where the current might bend the other way. Each discovery opened the door to more unsettling possibilities. Scenarios where causality frayed, memory dissolved, and the very notion of past and future blurred into ambiguity. The two-headed arrow some cosmologists proposed that the Big Bang was not the beginning of time, but a central moment from which two arrows diverge. In this model, entropy increases away from the Big Bang in both directions. On one side lies our universe, where time flows as we know it, forward, disorder growing. On the other lies a mirror universe, expanding in the opposite direction. where entropy also grows, but time flows backward relative to hours. From within each universe, inhabitants would feel the same certainty, memory of the past, ignorance of the future, entropy rising. Yet to each, the other would appear reversed. Two arrows, born from one origin, pointing away like reflections in a cosmic mirror. If true, then time's arrow is not singular, but doubled, a two-headed river flowing outward from the same source. A mirror universe next door, this idea echoes. Another speculation, that perhaps a mirror universe exists alongside our own, not behind the Big Bang but beside it, governed by the same physics, but with time reversed. In such a cosmos, what we call decay would be growth, what we call the past would be their future. Their light might still reach us, but scrambled, indistinguishable from background radiation. If such a realm exists, its imprint may be faintly visible in cosmic anomalies, alignments in the microwave background, unexplained asymmetries in particle behavior. This possibility is no longer mere philosophy. In recent years, researchers have speculated about mirror matter and anti-universes, scenarios that could reconcile certain puzzles in cosmology. The arrow of time, in this view, is local, not universal. One universe flows one way, its twin flows the other. Black holes, horizons of time. The river of time grows most turbulent at black holes, where space-time curves towards singularity. At the event horizon, time for a distant observer seems to slow, approaching a standstill. Inside, equations lose meaning. Some theorists suggest that beyond the singularity, time may flip. The collapse of matter into infinite density could, in some hidden description, mirror itself as a new expansion, with time reversed. In this view, the death of a star might seed not only a black hole in our universe, but a new universe on the other side. Flowing backward in its own arrow, the black hole becomes not just a furnace of entropy, but a gate between directions of time. Wormholes and closed time-like curves. Einstein's equations permit strange geometries. Wormholes, tunnels through space-time, connecting distant points. In some solutions, these tunnels can create closed time-like curves, paths through space-time that loop back upon themselves. In such a universe, time is not a line but a circle. Events repeat. Causes give rise to effects that loop back into their causes. A traveler could, in principle, move into their own past, raising paradoxes that unsettle reason itself. Physicists like Kip Thorne have studied these possibilities, showing how exotic matter might stabilize such wormholes. Stephen Hawking countered with his chronology protection conjecture, suggesting that nature forbids such loops to preserve causality. But the fact remains, general relativity allows them. The river of time, in its geometry, can coil upon itself. If such loops exist, then the arrow is not only fragile, it is negotiable. Time could fold, reverse, and reconnect, weaving a tapestry where forward and backward lose meaning. Causality at the brink. The greatest threat posed by these scenarios is not simply reversal, but the collapse of causality. Science rests upon the chain of cause and effect. A stone falls because it is released. A star explodes because fuel is spent. An action produces a consequence. If time can run backward, then cause and effect blur. Effects might precede causes. Futures might shape pasts. In quantum experiments, hints of this blur already appear. In delayed choice setups, the act of measurement seems to determine not only the present, but the interpretation of the past. Though no information is transmitted backward, The logic is unsettling. Reality appears to be written from both directions. At once, in cosmology, if time flows backward in other regions, then the foundation of causality is provincial. Our arrow is not a universal law, but a local current. This prospect is terrifying, for it unravels the explanatory chain that makes science possible. Without causality, knowledge itself dissolves. The fragility of the arrow-as, the investigations, deepened. One truth became clear. The arrow of time is not invincible. It is fragile, contingent upon entropy, boundary conditions, and symmetry violations. It is not enforced by the bedrock of equations, but emerges from improbable beginnings and delicate asymmetries. This fragility means the arrow might not be universal. It may bend, break, or reverse under conditions unlike our own. At the edge of black holes, in the infancy of the cosmos, or across a mirror universe, the current may run the other way. What was once the most certain of certainties, that time flows forward, became the most precarious. The emotional weight of reversal for scientists, this deepened the mystery. For philosophers, it deepened the dread. If time can reverse, then memory, identity, and history lose their footing. If causality collapses, then reason itself may falter. Yet for some, the idea carries strange comfort. A universe where time can reverse is a universe not confined by endings. Death may not be final, histories may not be absolute. Somewhere, perhaps, lives unfold in reverse, ashes drawn into flame, shards rejoining into vessels, the old becoming young. The silence of entropy unraveling into the order of beginnings. To imagine such a world is to glimpse a reflection in the dark mirror of physics, a universe where the arrow bends, and the river of time flows against itself. The deepening mystery, by now, physics had revealed too much to retreat. The equations permitted reversibility. CP violation demonstrated asymmetry. Cosmology suggested arrows could diverge. Relativity allowed loops. Black holes hinted at reversals. Time, the most certain of dimensions, stood revealed as uncertain. Its arrow, once thought absolute, appeared conditional. Its flow, once thought universal, appeared provincial. The mystery deepened. What seemed the most familiar became the most strange. The river of time, trusted to carry all things forward, might in truth be a delta, branching, looping, reversing, and flowing into directions yet unseen. The investigation had carried science to the edge of certainty. The arrow of time, so absolute in daily life, had revealed itself to be fragile, not carved into the laws of physics, but emerging from improbable beginnings and delicate asymmetries. To move further meant stepping beyond what could yet be proven, into the realm where equations become visions, where science blends with speculation. From the paradox of entropy to the vast multiverse, theories arose to explain not only why time flows forward, but why it might also flow back. Entropy and cosmology, Penrose's cyclic, Ian's Roger, Penrose proposed. A vision as audacious as it was. Haunting, conformal, cyclic cosmology. In this model, the universe does not begin or end. Instead, it passes through successive eons, each one born from the ashes of the last. The distant future of one universe, emptied of matter and dominated by radiation, becomes through a mathematical transformation indistinguishable from the Big Bang of the next. Time's arrow, in this picture, is not absolute but cyclical. Entropy grows within each eon, yet resets across the boundary. In the cold glow of the cosmic microwave background, Penrose believes he has seen faint imprints of the eon before ours, concentric circles marking collisions of supermassive black holes in a universe older than our own. If true, the arrow of time is not a straight river, but a wheel turning eternally. What flows forward in one age may loop into another, erasing the distinction between beginning and end. The Wheeler-Feynman absorber theory in the mid-20th century. John Wheeler and Richard Feynman proposed a radical reinterpretation of radiation, that electromagnetic waves are not only emitted forward in time, but also backward. In this absorber theory, when an electron emits a photon, it sends waves both into the future and into the past. The future absorber responds, sending its own wave backward, and the interference of the two gives rise to the radiation. We observe, this bidirectional dance preserves time symmetry at the most fundamental level. The radiation we see is not just a forward emission, but the result of an interaction stretching across time itself. If such a description is true, then causality is not unidirectional. Every event is shaped not only by what has come before, but by what lies ahead. The present becomes a negotiation between past and future. Retrocausality in quantum mechanics, with its paradoxes of measurement, offers fertile ground for speculations about retrocausality. In delayed choice experiments, a particle seems to decide whether to act as a wave or a particle only after the measurement is chosen, as though the present choice reaches back to shape the past. In the quantum eraser, the act of erasing information alters whether interference appears, even retroactively. Physicists debate whether these are true retrocausal effects or simply reinterpretations of quantum uncertainty, but the experiments carry an eerie message. The line between before and after is thinner than we imagine. Some interpretations, like the two-state vector formalism, even describe quantum systems as being determined by conditions both in the past and the future. Reality, in this picture, is a tapestry woven from threads extending in both directions along the river of time. The multiverse and reversed arrows inflationary cosmology suggests that our universe may be only one bubble in an endless multiverse. In some bubbles, the laws of physics may differ. In others, time's arrow itself may reverse. If entropy increases away from the origin in each bubble, then universes could emerge back to back, with arrows pointing in opposite directions. To each set of inhabitants, time would feel as real, and forward as it does to us, though from outside. The two would appear reversed. This speculation carries echoes of the two-headed arrow hypothesis, but multiplied into infinity. A cosmic foam of universes, some flowing forward, some backward, each convinced of its own certainty, none aware of the others. If such a multiverse exists, then our arrow is not a universal law, but a parochial feature of one bubble among countless others. Symmetry as the deeper lat, the core of these theories, lies a conviction that time's arrow is not fundamental, but symmetry is. The CPT theorem guarantees that if charge, parity, and time are all reversed, physics remains invariant. The Wheeler-Feynman theory restores symmetry to radiation. Retrocausal interpretations restore symmetry to quantum mechanics. Even Penrose's cycles suggest that time itself may be symmetrical when viewed across eons. Perhaps then, the true law of the universe is not the arrow, but the balance. Time flows forward for us because entropy rises here. But elsewhere, under different conditions, it may flow the other way. And the deeper truth is not the direction of flow, but the symmetry of possibility. false vacuum decay, a reset of time. Another speculative idea emerges from quantum field theory, the possibility that our universe exists in a false vacuum, a state not at the lowest possible energy. If the vacuum decays, tunneling into a lower state, the fabric of reality itself could change. Constants would shift, particles would transform, and the arrow of time might reset. In this scenario, the flow of time we experience is contingent on the stability of our vacuum. If it collapses, a new arrow may emerge, perhaps flowing in the opposite direction. It is a chilling thought that the river of time is not eternal, but vulnerable and could be rewritten in an instant. The river as branching and braiding taken together. These speculations suggest that the river of time may not be a simple current. It may branch into multiple streams, loop into circles, braid with countercurrents, or flow outward from a single source in opposite directions. Entropy explains its local course, but symmetry permits alternatives. Quantum mechanics hints at threads, woven both forward and backward. Cosmology hints at cycles and mirrors. Particle physics hints at asymmetries that give the arrow its tilt. The image that emerges is not of a single river, but of a vast delta, splitting and joining, flowing in ways our intuition cannot follow. The human confrontation with speculation for humanity. These theories are more than abstract visions. They strike at the core of existence. If time can flow backward, then memory, causality, and identity themselves are conditional. If universes exist where the arrow runs the other way, then our sense of forwardness is provincial, not cosmic, and if entropy resets across eons, then there is no true beginning or end, only cycles upon cycles, lives within lives, time itself, renewing like a phoenix. Speculation does not mean certainty, but it carries weight. It reveals that time, the most intimate of realities, is also the most mysterious. Its arrow may not be inevitable, its river may not be straight, and in its currents may lie the deepest truths of existence. Speculation carries the imagination far, but science demands more than visions. To know whether the arrow of time is fragile or fundamental, experiments must be devised, instruments built, and observations made with patience measured in decades. Across laboratories and observatories, humanity has begun to test the possibility that time may not be what it seems. The search for reversal, for asymmetry, for cracks in causality, has become one of the most delicate and ambitious frontiers of modern science. Particle accelerators, testing symmetry at the smallest scales, the most direct tests of time's arrow, occur in the subatomic world. At CERN, Fermilab, and Keck, beams of particles collide at near-light speed, creating fleeting states of matter. Among these, physicists study kaons and bemesons, the same particles that revealed CP violation in the 1960s. Experiments at the Large Hadron Collider's LHCb detector probe these decays with exquisite precision, searching for tiny asymmetries that could signal deeper time reversal violations. Every fraction of a second, billions of collisions produce data, and hidden in that storm are the rare events where nature whispers its bias between past and future. If CP violation is fully mapped, it may not only explain why matter triumphed over antimatter after the Big Bang, but also confirm that the arrow of time is encoded in the very particles that build the cosmos. Neutrino experiments, ghosts of asymmetry neutrinos, the ghostly particles that pass through the Earth by the trillions. Each second may carry another key. These shape-shifting particles oscillate between identities, electron, muon, and tau, as they travel, in experiments like T2K in Japan and NOVA in the United States. Beams of neutrinos are fired across hundreds of kilometers, their oscillations carefully measured. Soon, the Deep Underground Neutrino Experiment, DUNE, spanning from Fermilab to the Sanford Underground Research Facility in South Dakota, will attempt to detect whether neutrinos and antineutrinos oscillate differently. If they do, it would be a sign of CP violation in the neutrino sector, another crack in temporal symmetry. This could solve the riddle of why matter exists at all, and hint that the river of time is not impartial but tilts, ever so slightly, in one direction. Black holes and the edge of time and cosmic scales. Black holes remain laboratories of paradox. The Event Horizon Telescope, an Earth-sized array of radio observatories, captured the first image of a black hole's shadow in 2019, but its deeper purpose is to study how matter and energy behave at the brink of the horizon, where time distorts most severely. Gravitational wave observatories LIGO, Virgo, and KAGRA detect the ripples from black hole mergers. In those signals may lie clues to how information is preserved or lost, and whether time's arrow bends at the edge of singularity. If Hawking radiation can be detected or its properties inferred, it may answer whether information flows forward only, or whether it can also seep backward across time's horizon. Quantum experiments, probing retrocausality in the quiet halls of quantum optics labs. Lasers and detectors probe time in subtler ways. Delayed choice experiments, first envisioned by John Wheeler, have been performed with increasing precision. In them, a photon seems to decide whether it traveled as a wave or a particle only after the experimenter chooses how to measure it. Quantum eraser experiments go further, erase or restore information about a photon's path, and interference patterns appear or vanish retroactively. Though no usable signal travels backward in time, these results suggest that reality does not unfold in neat sequence. Instead, it seems to crystallize only when past and future are both taken into account. Physicists debate whether this is true. Retrocausality, or simply a quirk of quantum formalism. But the unsettling possibility remains. Quantum mechanics may weave the present from threads, extending in both directions. Cosmological observatories, time written in the sky on the grandest scale. Cosmology seeks the origin of time's arrow in the universe itself. Telescopes, like the James Webb Space Telescope, the upcoming Euclid mission, and the Vera Rubin Observatory peer into the distant past, watching galaxies form from the faint light of the first stars. If the arrow of time arises from the universe's initial conditions, then evidence must lie in its earliest structures. The cosmic microwave background, mapped by Kobe, WMAP, and Planck, shows a universe of low entropy at its birth. But anomalies in that radiation, cold spots, alignments, asymmetries may hint at a deeper truth. Perhaps our arrow is not universal but regional, one current among many in a wider ocean of time. Future missions may probe these anomalies further, searching for signs of mirror universes or hints of entropy flowing in other directions. Supercomputers, simulating other arrows where telescopes and detectors cannot yet reach. Supercomputers attempt to go. With billions of calculations each second, physicists simulate universes with varying initial conditions. Some begin in chaos, some in order, some with entropy rising, some with entropy falling. These digital universes allow researchers to test whether arrows of time can emerge from pure mathematics, and under what conditions reversals might occur. Though no simulation can prove reality, they serve as laboratories of imagination, guided by equations and constrained by possibility. The frontier of testing science balances on a knife's edge. On one side lies humility, the acknowledgement that time's arrow may be only emergent, its reversal beyond current proof. On the other lies ambition, the drive to build instruments sensitive enough to detect its cracks, to map its flow not only here but everywhere. The experiments are delicate, the signals faint, the risks of misinterpretation great, but the rewards are profound. To confirm that time's arrow can bend or reverse would be to rewrite our understanding of reality, to show that the most basic of certainties is not fundamental after all. A collective effort from CERN's colliders to new tunnels, from black hole observatories to quantum labs. The search is global. Nations and generations join in this quest, united by the desire to understand time itself. Each experiment is a fragment, each measurement a clue. Together they form a mosaic of inquiry, a portrait of humanity asking its oldest and deepest question: why does time flow the way it does? And hidden within that question lies the haunting possibility. Perhaps time does not only flow forward. Perhaps, in regions unseen, the river bends against us. Time is the medium of human existence. It carries memories into the past, pushes choices into the future, and frames every heartbeat within the certainty of forward flow. To live is to move with the river, to accept that moments arrive, fade, and are gone. Yet physics has revealed that this river may not be absolute. Its current may be fragile, its arrow emergent, its direction uncertain. The discoveries are scientific, but the implications are human. The fragile certainty of forward flow, if the arrow of time is born only of entropy, then it is not fundamental. It is the result of a chance beginning, a universe improbably ordered. At its birth, if CP violation encodes asymmetry into the particles of matter, then it is faint, not universal. If quantum mechanics hints at retrocausality, then the line between cause and effect is blurred. The forwardness of time, so intimate to experience, is revealed to be fragile, contingent, precarious. It is not a law written into the equations of nature, but a feature of circumstance. And in that revelation lies unease. If the arrow is fragile, then it may not hold everywhere. What becomes of causality? If time can reverse causality itself, is shaken. Cause and effect are the scaffolding of reason. To say that the present is shaped by the past is to anchor meaning. But if the arrow bends, then effect may precede cause. Memory may become anticipation, and explanation itself may dissolve. In quantum mechanics, the possibility already whispers. In cosmology, the arrow may diverge. If universes exist where entropy flows backward, then beings there would live lives as certain of forward time as we are, though their forward is our backward. Causality, then, is not universal. It is local, provisional, a law that holds only within the current of one arrow, not across the ocean of all possible times. The paradox of experience, yet, for all the equations and experiments, consciousness remains stubborn. The mind feels time's flow. Memory accumulates in one direction. Anticipation points the other way. Experience is inseparable from forwardness. Why should this be so? Some suggest that memory itself is entropy, the brain recording information as disorder increases. Others argue that consciousness is shaped by evolution within a forward-flowing universe, and so cannot imagine otherwise. Perhaps, if time reversed, beings within that current would feel as we do, convinced of forward flow, though their direction is opposite to ours. The paradox is profound. Physics may see time as symmetric, yet life insists on asymmetry. Between the two lies the deepest of mysteries: why the universe feels the way it does, humanity's place in the river for humanity. These revelations are both humbling and haunting. To measure the cracks in time's arrow is to touch the foundations of existence. From Brookhaven's kaons to LIGO's black hole signals, from neutrino tunnels to the microwave sky, we have begun to probe not only matter and energy, but the current of reality itself. That a species on a fragile planet can even ask whether time flows backward is extraordinary. It is a triumph of curiosity, of reason reaching beyond survival into eternity. Whatever the answer, the act of questioning binds humanity to the cosmos, not as passive passengers of the river, but as conscious witnesses of its mystery beyond. Beginnings and endings. The arrow of time is not universal. Then beginnings and endings themselves are illusions. A universe that flows backward is as real as one that flows forward. Eons may succeed one another in endless cycles. Black holes may birth new universes, each with its own arrow. The multiverse may teem with bubbles, each with its own direction. In such a vision, the idea of a single origin dissolves. The Big Bang is not the absolute beginning, but a transition, a point where arrows diverge. Eternity is not infinite forwardness, but the coexistence of flows in every direction. To contemplate this is to confront eternity in its strangest form, a cosmos larger than time itself, the poetry of reversal land. Yet there is poetry in the thought of reversal, in imagining a universe where ashes rise into flame, where the old become young, where entropy unwinds into order. Though physics may forbid such scenes in our world, their possibility in others is a mirror held to existence. It reminds us that our certainty is not absolute, that what we call inevitable may be contingent, that what we call the end may elsewhere be the beginning. To think of time flowing backward is to glimpse the fragility of reality and the creativity of the cosmos. Final meditation. The river of time has carried humanity from starlight into consciousness, from ignorance into wonder. It feels unbreakable, but physics has revealed its cracks. Entropy, symmetry, quantum uncertainty, all whisper that the arrow is not law, but circumstance. If so, then the universe is stranger than we dare imagine. Time may not be a straight current, but a braided delta, flowing forward here, backward there, looping, branching, converging. Past and future may not be absolutes, but perspectives. What does this mean for humanity? It means that existence is not bound by inevitability, that reality is larger than memory, larger than anticipation, larger than the single current we inhabit. It means that in seeking to understand time, we confront the deepest of truths, that the universe is not only space and matter, but also mystery, a mystery written in the flow of time itself. And perhaps the greatest mystery is this, that the river of time, which seems to carry us forward, may also, somewhere beyond sight, flow backwards, carrying with it lives histories, and worlds that move against our current, as real as our own, yet forever hidden beyond the bend of eternity.